So we're talking about polygons in general. So we're going to start with a bunch of vocabulary first. Most of this vocabulary you're familiar with, you've done it before. A couple of things are kind of new and really important to the stuff that we're going to be doing. Polygon, for starters, is a closed plane figure. Now, plane figure means it exists in an endless flat plane, right? A plane is an endless flat surface. So basically that word plane just means that it's not three-dimensional. It's two-dimensional, flat. Okay? So it's got straight sides and at least three sides and angles. There are interior angles of a polygon and there are exterior angles of a polygon. Obviously interior on the inside, you can see by this diagram. Exterior angles, if you remember, we talked about exterior angles of a triangle. Remember this theorem, the exterior angles theorem of a triangle says that one exterior angle equals the sum of the two remote interior angles. Remember that? Right? So we did talk about exterior angles of a triangle. That theorem only applies to triangles, but the term exterior angle can be any polygons. And exterior angles are always formed by extending one side of the polygon, and then that angle that's there, what's the relationship of that exterior angle to the interior angle? Supplementary, because it forms a linear pair. I would like you to write that actually. Each exterior angle forms a linear pair with an interior angle. Ugh, I just don't know why this is not working for me. Okay. There we go. Each exterior angle forms, oh my gosh, a linear pair with an interior angle, which makes them supplementary. Okay, convex and concave. You've probably heard these words before. Polygons that we're used to using and drawing and solving are typically convex polygons. A concave polygon is a polygon that looks like it's kind of caved in. It looks like somebody's like denting the side of it. It's got an exterior angle that's like obtuse. Okay, so mostly we're going to be dealing with convex polygons. All right, these three words. You've definitely heard equilateral, means all the sides are equal, and equiangular, which means all the angles are equal. But this might be new. A regular polygon. This is actually a really important concept and term that we're going to be using a lot. A regular polygon is a polygon that's equiangular and equilateral. So it's really special. A regular polygon has these qualities that are really special. If we know something's regular, there's a lot we can figure out about it. And you're going to see that later. Okay, so the word regular typically means like not very special, you know, like, oh, it's just a regular old day or whatever. But you got to remember that regular in geometry terms is really special. We've got all the sides the same and all the angles the same. I think it's called regular because typically, like if I said to you, you know, close your eyes and picture a hexagon, you would probably picture this, right? You probably wouldn't picture that. Right? That is 6 sides, and it's a hexagon, but that's not typically what you think of when you think of a hexagon. You think of a regular hexagon, right? But remember that there's really special properties to that. Okay, a diagonal. Again, this is a word you've heard before. You've probably drawn the diagonal of a rectangle before. But by definition, a diagonal of a polygon is a segment that connects two non-consecutive sides. Two non-consecutive vertices. If I connected consecutive vertices, what would I be drawing? Just the side of the polygon, right? So a diagonal does not connect consecutive, because that would be a side. It connects non-consecutive vertices. So when you have a square like this, I can draw a diagonal that way. I can draw a diagonal that way. But that's it, right? But what if I have an octagon? In an octagon, if I go to this vertex, I can draw 1, 2, 3, 4, 5 diagonals from that one vertex. So how many diagonals are there altogether? Seems like there'd be 40, right? Why is there only 20? Because you can't count them twice, right? So from there, I could go to the next. I really missed that one pretty badly. But if I go to the next one, again, I can do 5. Change colors. 1, 2, 3. Oh, wow, I'm really off. 4, 5, right? But when I go to the next one, look, I already have a green one right there. So I can't count that again. So that's why it turns out to be 20. Yep. Okay. So sometimes we're going to just draw the diagonals from one vertex, and that will have some significance. We're going to do that on the next page. But if you drew the diagonals from all the vertices, there's quite a few of them. Notice that in a concave polygon, sometimes the diagonal is on the outside of the polygon, which seems kind of weird, right? But like PQ, technically, by definition, is a diagonal of that concave polygon. Okay, so let's look at this chart here. We're going to fill this chart out left to right, kind of one column at a time. So along the left, you have a picture, a diagram of all these different types of polygons. What I want you to do is fill out columns 1 and 2 first. I will start you off. This polygon is called a triangle. Hopefully we all know that by now. And it's got 3 sides. This one, don't call it a square or rectangle. It's got 4 sides, and the word for 4-sided polygon is quadrilateral, right? So let's call it a quadrilateral. And it's got 4 sides. Okay, continue down the left and fill those in. Okay, so we've got pentagon, hexagon, septagon, also can be called a heptagon, septa or hepta, either one is fine. Octagon and nonagon. Now, I know there's not a lot of room here, but I want you to kind of draw a line right there. And I'm going to have you add 2 that I need you to be responsible for knowing. Okay, so I want you to be able to name all of these, plus know a decagon, D-E-C-A, is a 10-sided figure, and a dodecagon is a 12-sided figure, right? Do means 2 and deca means 10, so together it's 12-sided figure. Anything that's not on this list you can call an n-gon. But in the place of n, you would put the number of sides. So in other words, like a 13-gon is a 13-sided figure, etc. A 50-gon is this polygon with 50 sides. Okay? But those special names, these are the ones I want you to know. All right, let's go back up now, and this next category, this next column, says the number of triangles formed when drawing the diagonals from one vertex only. So draw the diagonals from one vertex. I'm actually going to start you off on the pentagon. So skip to the pentagon for a second. Drawing the diagonals from one vertex means I'm going to draw to here and to here. That's it. I can only draw two diagonals. How many triangles are formed? 3. Okay, so if I go back to triangles now, how many diagonals can I draw in a triangle? 0. How many triangles are formed? 1. How many diagonals can I draw in a quadrilateral? From one vertex. Only 1. So how many diagonals, how many triangles are formed? Okay, you're going to see a pattern here. Finish that column. Okay, so I would like you to also fill in this category, this last one here, right? An n-gon, a regular n-gon, has n sides. N is what we use as the number of sides. So then the number of triangles formed could be expressed how? Using n. Yeah, n minus 2. Every single number in that column is 2 less than the number of sides. You guys see that? Yes? Okay. All right, so let's go back up here now. What is the sum of the interior angles of a triangle? The sum of the interior angles of a triangle. 180. We've been doing that since we learned triangle sum theorem, right? 180 degrees. Okay, what is the sum of the interior angles of a quadrilateral? 360, which you already knew. But let's look at it in relation to these triangles and see why this makes sense. We've got these 3 angles in this triangle add up to 180. And these 3 angles also add up to 180. So it makes sense that since there's 2 triangles in a quadrilateral, that's how the angles add up to 360. So you can think of this 360 as being 180 times 2, basically. Right? Okay, so if we get to a pentagon, we're going to do 180 times what? 3, because there's 3 triangles. And what does that come out to? Okay, finish that column. So there's the rest of the sums for this chart here, but how could we fill in a formula basically using n for getting the sum of the interior angles of a polygon? Yeah. Good. So 180 times parentheses n minus 2. That's the sum of the interior angles of a polygon. And that works for regular or non-regular polygons. That works for all polygons, all closed plane figures, right? No matter how many sides, you do 180 times 2 less than the number of sides, and you will get the sum of the interior angles. Okay, this last column says, what is the measure of each interior angle? Well, we can't know that if it's not regular, right? Because they could be split up all unevenly. But if we know that it's a regular polygon, then we could figure out the measure of one interior angle, knowing that they're all the same in a regular polygon, if we have that the sum is given to us. So in this column, if I have a triangle, it's 180 degrees total. If I split that into the three angles equally, how many degrees will each angle be? 60 degrees. So how are we going to get the measure of each interior angle of a regular quadrilateral? What are we going to do? So 360, the total number of degrees on the interior angles, divided into 4 equal angles. And that's going to give us 90 degrees. Let's do one more. Pentagon, total of 540 degrees, split into 5 equal pieces. Okay, so continue filling out that column there. Okay, so the measure of each interior angle should be that last column there, but how could we write a formula for that? Again, in terms of n, what did we do to get the measure of each interior angle? Ella? Good. The sum of the interior angles is 180 times n minus 2. Divide by the number of sides, and that's how we got the measure of each individual interior angle. Remember, that can only be used if it's a regular polygon, because that's assuming all the angles are the same. Any questions? All right, let's look at the next page. So this top box basically summarizes that into a theorem. The sum of the interior angles of any polygon is 180 times n minus 2. So we can use that to figure out missing information. So number 1a says find the sum of the interior angles of an octagon. Now I know we already did that, but let's put it into the formula. If our formula is S equals 180 times n minus 2, and we're asked about an octagon, what's n? 8. So essentially, it's going to be 180 times 8 minus 2, which we just did on the other side of this notes, right? Sum of the interior angles of an octagon was 1080. Okay, but this next question is a little bit different. Kind of reverses the process. How many sides does a polygon have if the sum of the interior angles is 1980? So we're going to use our formula again, or our equation. The sum equals 180 times n minus 2. This time, we don't know what n is. We have to solve for n. Where do we put the 1980? In for s, right. So this is going to be 1980 equals 180 times n minus 2. And then we're going to solve for n. How would you solve for n? What's the first step that you guys would do? Yep. Okay, so I heard two things. I heard distribute, and I heard divide by 180. Both are correct. You can do it either way. Okay. I am going to distribute first. 180n minus 360 equals 1980. Add 360 to both sides. Divide by 180, and n equals 13. All right, let's compare that to if we had divided by 180 first, which is also correct. $19.80 equals 180 times n minus 2. Divide both sides by 180. You get n minus 2 equals 11. And then what? Add 2 to both sides. So, same answer, algebraically, both correct. One is not better than the other one. You can pick your favorite. I will tell you this. Historically, my experience is that people who do the distributive property first make less mistakes on one like this. Personally, I prefer this method. So, I'm not saying one's better than the other, but I will caution you against this left method. I'll tell you the mistake that people make. People get to this point, 11 equals n minus 2, and then quick in their head, they get that n is 9. Because they do like 11 minus 2. They get 9. And of course, they get their test back and they're like, oh, that was a dumb mistake, right? So just be careful that you're not going so fast that you subtract 2 instead of add 2. Or sometimes people even just put 11 as their answer because they're like, oh, I'm done. Okay, so just be careful with this method. I just find that there's mistakes sometimes. Yep. Yep. Okay, so part C. Oops. The measure of angle y. So this is similar to the homework you had last night where you were finding the sum of the interior angles of a triangle and then finding the missing angle or variable, or the sum of the interior angles of a quadrilateral. But now this one's a pentagon. So you knew that triangles were 180 and quadrilaterals were 360. Pentagons now are what? Add up to how much? 540, right? Because it's 180 times 5 minus 2. So the total sum is 540. So when we find what y is, we're just going to do 110 plus 90 plus 120 plus 150 plus y equals 540 degrees. And basically, you're solving for y. You have to add those all up, subtract from 540, and you'll get your answer, which is 70 degrees. Okay, I'm going to have you do the number 2, A, B, and C on the right-hand side here. Everything is modeled on the left-hand side, so it should be pretty easy. All right, so these should be the answers. The sum of the interior angles is 900. This polygon has 20 sides. Again, it's done just like we did on the left. And then the last one is 102 degrees. Any questions on that? Okay, so the next concept is actually much simpler. And that is that the sum of the exterior angles in a polygon is always 360 degrees. The sum of the exterior angles of a polygon, no formula necessary, it's always 360 degrees, which is kind of amazing, right? If you take a triangle and you extend the sides, and you make 3 exterior angles. You add them up. Even if it's not a regular polygon, nothing special about it, add them up, it's 360. Here we have a quadrilateral. Same thing. Extend all of these to make a linear pair. Nothing special about this quadrilateral. Add up the exterior angles, it's 360. This will work no matter how many sides. 50 sides. All the little tiny exterior angles will always add up to 360. All right, so that makes our calculations and our math a little bit easier with exterior angles. Keep in mind that an exterior angle forms a linear pair with an interior angle. So this is actually going to help us with some interior angles as well. All right, before we work through this side, I want you to add a couple of things here, because it's worth noting that if in a regular polygon, two things can be calculated using the fact that it's 360 degrees. Each exterior angle. Let's think about that. You know they add up to 360 degrees. Let's say it's a decagon. How many degrees is each exterior angle? How would you calculate it? 360 divided by 10, right? Because if it's a decagon, there's 10 sides, which means there's 10 angles, which means there's 10 exterior angles. And if they all add up to 360, and each one of them is equivalent to the next, 360 divided by 10 will get you the number of degrees in each exterior angle. So each exterior angle we can think of as 360 divided by n. Well, similarly, if we just take that same equation, really, what happens if we want to solve for the number of sides in a regular polygon? Well, the number of sides is just going to be 360 divided by each exterior angle. Right? So similar to that problem we just did, if I know that there's a regular polygon and each exterior angle is 10 degrees, each exterior angle is 10 degrees, and I say, well, how many sides? Well, if we know they add up to 360 and each one is 10, we can just do 360 divided by 10, and that will give us the number of sides. Does that make sense? Yes? Okay, so that's applied right here. What is the measure of each, or one, or n exterior angle of a regular nonagon? Well, nonagon is how many sides? So we're going to do 360 divided by 9, and each exterior angle is going to be 40 degrees. Number 4 is the same exact thing. What is the measure of each exterior angle of a regular 18gon? 360 divided by 18 is 20 degrees. This one's different. This one says find the measure of each interior angle of a regular nonagon. This is where I want you to pay close attention. 2 pages ago, we had a column that said the degree measure of each interior angle of a regular polygon can be found by doing 180 times n minus 2 divided by n. In other words, find the sum of the measures of the interior angles and then divide by the number of sides, and that will get you each interior angle. But I don't want you to do it that way. How else could we do it? I'll give you a hint. It's all right here. Yep. Okay, good. It's actually easier to find the exterior angle measure and then know that it's supplementary to the interior. So we just did each exterior angle of a regular nonagon is 40 degrees. So what's the interior angle going to be? 140. The individual cells of a honeycomb are regular hexagons. What is the measure of one interior angle of a honeycomb cell? Now, I know this is hexagons, and we could look back a couple pages, but let's show the calculation for this. Yep. Yep. So, we're going to do 360 divided by 6, because 6 is the number of sides in a hexagon. We're going to get 60 degrees equals an exterior angle. Right? So how do we get the interior angle? 180 minus that. Okay? So the idea is to use the fact that the exterior angle is a little bit easier. Okay, number 7, if the measure of an interior angle of a regular polygon is 150, how many sides does it have? So again, we could do this math because that's the formula for the interior angles, one interior angle. Or we could use the fact that it forms a linear pair with the exterior angle. So imagine we have this regular polygon. We don't know how many sides it has. But we do know that the interior angle is 150. So what's the exterior angle? 30 degrees. How could we get the number of sides? Yep, 360 divided by 30, because all the exterior angles add up to 360, and each exterior angle is 30. 30 times 12 is 360, so 12 sides. Okay, so this first practice problem is just vocabulary. What are the exterior angles for angle 1? Which angles would be considered exterior angles to angle 1? Yeah. Go ahead, Nick. Angle 4 and angle 2 are the exterior angles because they form a linear pair with angle 1. So every angle actually has 2 possible exterior angles that can be formed. Number 2, your friend says that she measured an interior angle of a regular polygon as 130 degrees. Explain why this result is impossible. An interior angle was 130 degrees. Why is that impossible? Good. Perfect. So same idea that we did up here. If the interior angle is 130 degrees, this is what the friend is claiming here, then the exterior angle would have to be 50 degrees. And if it's a regular polygon, that means all of the exterior angles are the same. So we should be able to do 360 divided by 50 degrees and get the number of sides. But that comes out to 7.2. And we have 7.2 sides. Impossible. The rest of this packet is practice, okay? What I would like you to do during class right now is the left-hand column down both sides of that page, and then finish the rest for homework. But during class, I want you to get a sampling of every type of question so that if you have anything that you want to ask about or need help with, you can ask while you're still in the classroom, okay? Finish that packet for homework.